With the axial load, the scenario was very simple. We said it's going to create a normal stress. That normal stress, we call it sigma, and this sigma is simply force divided by A, or I'd better show it by F divided by A, which this F is the internal, again, load, which for this simple case, this internal load is equal to P, and A is the cross section. The second stress that we learned comes from bending. When we try to bend something, example, more like a beam, and the stress in this scenario, sigma, we simply calculate it by my divided by I, which I was moment of inertia about neutral axis, and neutral axis basically on a cross section, which we show it by NA, is an axis which passed through the centroid of an area, right? Centroid. We learn how to find centroid, and also we learn how to find I, moment of inertia, about this axis. And this Y is the distance from the point we want to calculate the stress. The further we are away from this neutral axis, the larger this stress. And as you saw previously, we can draw these basically diagram for stresses, and we can, depends on the direction of the bending at portion of these cross section, it is tensional, and then another portion is compression, right? Like in this example on neutral axis, above the neutral axis it is under tension, and below it is under compression. The third type of stress that we just learned was torsional stress. We show it by tau. It is tau because the type of stress, unlike the previous two examples, like previous two scenario, we have the stresses normal to the plane. In case number one, stress is normal to the plane, normal to the cross section. The second one also, it is normal to the cross section. But for torsion, we learn the example of disc sliding on top of each other. It is on the surface. It is more like friction, and that's why it is tau. It is a shearing stress. And this shearing stress, we learn it, it's simply TR divided by J. As you saw in earlier lecture, R is the distance, the radius for the point we want to calculate the stress, which normally we calculate the stress for outer diameter or outer radius. And J is the polar moment of inertia. And eventually, something which we call it shearing stress. In early modules, you learn about shearing stress. And two examples that we can use this shearing stress is like this simple example that I showed, two blocks. I glue them together, and these two blocks, we apply load, and we want to slide them on top of each other. Instead of glue, if we use bolt, also when we try to apply this load, it's going to create shearing stress, which for the first scenario, let's say if this is the area that we glue things together, let's say this is the glue area. Then in order to cancel these, basically this force that we have here, we have to have also small shearing stress on this area, on the glue, right? And similarly, in example of a bolt, this time, instead of the whole area being glued together, we can imagine this bolt as be more like this gluing, but it's just a small portion which carry all the stresses, like on this small area, on this cross section of the bolt, right? And we learn for both of these scenarios how to calculate tau stress, which in this case tau was force F, if the force is F, divided by A, which in this example A is the whole area that we glue things together. And in this example, tau, the shearing stress for bolt, is again F divided by A, which A is this area of the cross-section of the bolt, basically. Another type of stresses, which belongs to the category of shearing, and you haven't learned it in this course, is shearing stresses for a beam, basically. If you recall, for a beam at any cross-section, you have internal loads M and V, right? Which you learn how to draw the diagram for this V and M. So this M results in a bending and bending stress, the second type, right? But this V, it's result in a shearing force. Again, if you forget, please go back to the module 5 when we talk about this shearing and bending. And you saw this shearing also, it creates a stress, which is a topic for Mech 360 in your future course, if some of you are taking it. And it has a formula, if you've seen somewhere, tau is VQ divided by IT. So I just write it down here, Mech 360. But it's not really a complicated thing. It's very simple to calculate. V, already you calculate V for each cross section. I is moment of inertia, similar to bending. T is the thickness or the width, basically. Let's say if I want to calculate the stress at point B, this is the thickness at point B. If somebody wants to calculate the stress at point A, then this is the width or the thickness of the cross section at that area. And this Q is, we call it the first moment of inertia. I just briefly mention this. So later, some of you, if you have 360, then you can show off to your friends because they are just about to learn it, but you know what it is. And if you don't, if you're not planning to take 360, then if in the future in a design or somewhere you saw this one, then you know what it is, all right? And it's not really complicated. So this Q, we call it the first moment of inertia, and basically Q is A multiplied by L. And A is the area. Let's say if I want to calculate stresses for point B, like on this cross section, A is going to be this area, and L is the distance between that area, center of that area, to the neutral axis. Remember, this is the neutral axis. Maybe I draw a bigger image here. So let's say this is your cross section. Okay, this is the cross section. And somebody asks you to find the stress at, let's say, this point. All right. So at that point, this is your thickness, and the area above that thickness, call it A, and then from the center of that area to neutral axis, we call it L, and from there we can calculate Q, which is called first moment of inertia. The reason that we call it first moment of inertia is because if you recall this I, we call it second moment of inertia. We don't want these two to get confused. Right, and this I had a like distance power 2, but this Q has like multiplied by L. But don't worry about this part. This is a portion that you don't need to study for Mech 260. And also in future, in design scenario, most of the time we ignore this tau. Like in most of the design that I do, I ignore this tau, because this tau is very, very small. Like in a beam compared with bending stress, this tau is just something that you can ignore it, like in a range of 100 times smaller. So if you base your design based on bending for a beam, then you are safe. You don't need to worry about these tau. It's very, very simple. Right? That's why it's not too much emphasis on this one. All right, so this is a summary of what we've learned so far. Always keep it in mind that you have a shaft. It is under 4 types of loading: tension or compression, torsion, bending, and shearing. All right? Shearing is more like you take a knife and try to cut this shaft from a point. Like a shearing force, try to cut it. All right? Which, with each of these loading, there is a stress. The stress can be a normal stress, which we show it by sigma, or it can be a shearing force, which we show it by tau. For each of these type of stress, we have a simple formula which you've learned, hopefully so far, how to calculate stresses, right? So now we want to combine all of these things together. But how we can do that? Let's say in a very, very general case, you have a 3D part, a member, which like I show it more like a weird shape. So trying to emphasize that it doesn't have to be any particular shape. It can be a cylinder, it can be a cube, it can be anything. Now, let me move myself up there so I have more room there. Okay. Now, let's say we are interested in finding the stress in a particular point inside that part, right? Inside, in the heart of this part. We want to calculate the stresses. And we know there are stresses because we have external loads. We know anytime that there are external loads, internally, things are under tension or compression or shearing, right? Which we call them stresses. So we want to figure out what is the stress at this point, whatever we want to call it, like a point inside. So I take it out, this point, and I magnify it, so then we can discuss it more. And also, we imagine that this point is more like a, let me get my pen here, okay. All right, so we imagine this point to be more like a cube shape. Again, for simplicity, it's a point, it's just tiny, it's very small, it's just a molecule or a crystal, right? And let's say we magnify it and it looks like, let's say something like this. If I try to draw something for you guys. And again, we don't have to draw it, consider it as a cube shape, but because it's a tiny point, for simplicity, we try to imagine this tiny point when we put it under microscope and magnify it, that it looks like a cubical shape. And now, because it is a cubical shape, like always, we consider basically 3 axes because we are in 3D. And let's say my axis here, I draw them above here, X, Y, and Z. So this is, imagine, is X, and this is Y, and this is, let's say, Z. All right? So in a general sense, we say when we apply these loads, this point or this cube is going to be under normal stresses on each of these faces in X, in Y, and in Z direction. All right? They might be under compression, but now for simplicity, we just show tension. So let's call this one sigma X, and call this one sigma Y, and call this one sigma Z. Also, because we are in a static, this point, or a better name from now on, we call it an element. And element. An element, it means a tiny, tiny cube from this part, right? This element has to be balanced. Otherwise, things start moving and it's not static, and we don't like that, right? So if I have a sigma x on this face, it means I have to have another stress on the other side of these. I have to have another one below, and I have to have another one over there, right? So if this one is sigma x, the other one is sigma x, sigma y, and sigma z, and they are in balance. And also, we know because of all this external loading, if we imagine this part as many, many elements like this, we stack them on top of each other and on side of each other, these cubes or this element may slide on top of each other, right? So there might be shearing stress as well. Let me draw the shearing stress for you. Shearing stress, I show them by blue. So let's say on this surface, for example, I might have a shearing stress like that one, okay? Because imagine there is another element or another cube on top of this one, and they try to slide on top of each other because of the external load, right? So what about shearing stress? If I have it in that direction, then probably I might have shearing stress in that direction as well, right? We don't know, maybe the shearing stress is both in X and in Y. What about this surface? Same surface, I might have something like that, or I might have something like that. Okay? So let's decide for a notation so we don't get confused. If I want to show this stress, this one, first of all, I show it by tau because it's a shearing stress, all right? And because I don't want to get confused between this tau and the other one, so this is something that we agree together. I put two letters here. The first one for the plane that this tau is. Like this tau is on a plane belong to y-axis. Probably in one of your math course or in your physics course, you learn each plane, we show it by a normal axis basically. And like the one at the top, it's a plane that is normal axis is y. So I call it tau y, and the direction is in x, so it's going to be tau y x. All right. So what about this one? This one is again tau. It is on a plane y, and its direction is z. So it's going to be tau y z. All right. And what about this one? This one is going to be tau, right? It's going to be tau. So which plane it is? It is on a plane x, and its direction is y. So it's going to be tau xy. And similarly, so this one is going to be tau. So it is on plane x, and direction is z, tau xz. Okay? So this is the way then we show the stresses for each side. All right? But, and on this side as well, we have maybe one going up and another one going there, which by now you probably figure out how to show them. For example, this one probably has to be z, y, right? Because it is on z-axis and its direction is y. And with the same concept that I told you for this sigma x, if this one is sigma x, the other side has to be sigma x because things has to be balanced, we are going to have the same story here. So if I have tau xy here on this side, on the mirror side, which we cannot see now, I have to have something going down and they have to be equal. Otherwise, things are not going to be balanced. Let me show it in a 2D so it makes sense more. Z, or let's say this is XY view. We are looking at XY, so or the Z view, all right? This is what we are viewing because it's difficult to show it here. So we agreed that if we have a sigma x here, we are going to have a sigma x there and sigma y there, and we're going to have a sigma y down there. And they are all equal. So this is sigma x, has to be sigma x, this is sigma y, this one has to be sigma y. Okay. And this one we agree that probably we have a tau xy here. If I have a tau xy here, I have to have another one here, but because we are in a static, the other one has to be the opposite direction, right? Remember, if this is sigma y, the other one is opposite direction because they have to cancel out each other. If I have tau xy, this one is coming down and it has to be the same magnitude. It has to be tau xy. Similarly, the one at the top, if we call this one tau yx, I have to have another one down there, canceling that one, and it has to be the same, tau yx. So this element is very small, but still it has a dimension, it has a length and width, which they are equal. This tau xy on the side, on the vertical side, try to rotate this element. How? They try to rotate it counterclockwise, right? Do you agree? Imagine they are more like couple, like this tau xy and tau xy on the vertical side. They try to rotate the element counterclockwise. So we have also these tau yx at the top and tau yx at the bottom, and they try to rotate the element clockwise. So because the element is balanced, because we are in a static, these two has to cancel each other. So we have no choice but tau xy to be equal to tau yx. Otherwise, this element starts rotating. So then we have a part that each point in it starts spinning, which is not possible, right, physically. So with the same, basically, justification, we can say tau xz, for example, is equal to tau zx, and tau yz, for example, is equal to tau zy. All right? So now if I say on each element, what do I have? I have sigma x, I write it down here. I have sigma y, I have sigma z, and then I have tau xy. I don't need to write tau yx because tau yx is equal to tau xy. I have tau xz and tau yz. All right? And normally we show all of these in a matrix form, which diagonal to be the normal stresses, x, y, z, and more like a matrix, this one becomes tau xy, this one becomes tau xz. See, the first row, it's all x, xy, xz. And this one is tau yz. Some people try to be more like meticulous and, let's say, more fancy. Even they put an x here, tau xx, sigma yy, sigma zz. Because in fact, on this element with the same concept that we said here, right? This sigma x is on a plane of x and its direction is x, sigma xx. But in this course, we just keep things simple and just write down sigma x, sigma y, and sigma z. And this matrix, based on what we just said, it's a symmetric matrix. In fact, this is like this matrix is symmetric around the diagonal. If this is diagonal, so this is symmetric. Because you just saw that tau, this guy is tau yx, but we just saw that tau yx and tau xy, they are equal, right? And similarly, this one is tau zx and tau zy. So this matrix is called the stress element, or state of stress, state of stress for a 3D element in general. It's a matrix 3 by 3. It has 9 elements, but it's symmetric. It means only we have 6 values: sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. And this is something we call it stress tensor. All right? If you recall, in module 2, I introduced the concept of tensor. I just mentioned the name, maybe you forget by now, but physical quantities, they can be a scalar, they can be a vector, and they can be a tensor. Scalar, just a magnitude. A vector, you need magnitude and direction. When it comes to tensor, you realize that you also need one more thing. You need to tell the people which plane you are. Are you in plane like the one at the top? Are you in plane like a vertical plane, like this one? Or you are on a plane which its normal axis is z-axis. You need to tell people which plane you are. And this is a quantity which we call it tensor. And stress is in a category of tensor, basically. But so far we didn't talk about tensor because all the cases we studied was like a simple case. We show it more like a vector, more like a direction. But from now on, you learn that the stress is a tensor. What about the sign? So for a sign, let me write it down here, stress sign, because I've seen a lot of time, student again, confused about this. So when it comes to sigma, it is either positive or negative, which we had an agreement, right? We said if it is tension, we show it by positive. If it is compression, we show it by a negative sign. What about tau? Do we have positive or negative? No. For shearing stress, no positive or negative. So it doesn't have any sign. But it has the plane, right? Am I on XY plane? Am I on YZ plane? So no sign, but we need to tell which plane. How do we say? For example, we say tau xy. When I say tau xy, immediately you visualize this cube and you say, oh, okay, tau xy is that. Even when I'm showing it in a 2D form like this one, that you see it here, in a 2D form, by tau xy, now immediately you say, okay, this is tau xy. My axes are x and y, and this is tau xy because of this concept that Ahmad told us, all right? Tau xy, tau xz, and so on, and tau yz. All right? So it may looks like a little bit complicated, but later you'll realize it's not really, all right? So one more time, you take any point, you magnify it, you imagine this point as being more like a cube shape because it's so tiny, it's just a point. this cube, we imagine the size and they are the same, like width, height, and depth. And then we decide for x, y, z. And on each side, we have shearing stress and also normal stress. So some of this number might be 0, depends on the problem. Some might be negative, like sigma x, sigma y, and sigma z. They might be compression and negative. There might be 0, which you will see examples soon. And the direction for tau, no negative, no positive, but we just say if it is xy, yz, or xz, all right? And this is what we call it, a state of stress for a 3D element. Let us stop here and see if you guys have questions, because you need to be clear about this part before we move forward. Are we good? All right. Now we want to simplify things a little bit. We want to see, can we switch to a 2D element? Because a 3D element is really ugly. It makes the calculation difficult. And if you recall, I told you like maybe 98% of the problem, practical problem, we can simplify them to 2D. You've seen many examples which in practice they are 3D, but we could simplify them by just looking at one view and we solve them as a 2D problem. Can we do it for a stress element? The answer is luckily yes. Two scenarios or two cases which we can we can simplify a 3D element to a 2D element. The first one is when we are looking at the stress in outer, basically, portion of an object, outside an object. So we have a 3D object. So this is the object is 3D, all right? And we are looking at outside of it, at a point outside. So what do we have outside? Outside is just air. Nothing else, no force, nothing, right? If there is nothing outside, there is nothing compressing this point, this cube, like on this surface of this cube, nothing to compress it, nothing to rub it, like slide something on top of it, then it's safe to say that all the stresses on this side, they are 0. 0 for an outside element. Because in fact, we don't have any things here, right? This element outside, that's the same surface here. And if I don't have any things, it's just air, it means all of these things are 0. So if all of these things are 0, we just said that tau zy is equal to tau yz, then it means this guy has to be 0, and this one has to be 0. So it means I can, now I'm dealing with an element which is basically everything in z-axis is 0, and I can simplify it by just showing the stresses in x and y. So that's that one. Other direction. If that one goes up, this one coming down, this one is going down, and this one is going down like that. All right, so this one is sigma x. This one is sigma x. This one is sigma y. And all of these, they are the same. They are tau x, y. And usually we write them down at the corner. Because remember, we said this is tau x, y. This is tau y, x. They are equal. The one at the top and bottom, they are equal. Because of the rotation things, we say they are also equal. So a 2D element with just 3 numbers, sigma x, sigma y, and tau xy. All right. The second scenario is we have a thin plate, like this one that I showed here. It's a very, very thin plate, let's say like a sheet of paper or a sheet metal, which is very thin. And the thickness is so small that we almost ignore the stresses on that small thickness, right? In that scenario, we say, well, we don't need to be worried about these depth, like this Z on this 3D element. We can, because it's so thin, we just ignore the stresses and we show it as a 2D element, as you can see it here. Right? So one more time, two scenarios which we can simplify 3D elements, get rid of it, and then work with a 2D element. One is when we are looking at the stress outside an element, which if you remember from the past lectures, again, most of the times we solve the stresses for outside, right? Because outside the stress is maximum. If something wants to break, it's a start from outside. Nothing start from inside unless there are complications like cracks and stuff, which is not the subject here. So if you are looking at stress outside, or if the things that we are analyzing is thin, very thin, like this one, we assume a 2D element. So for 2D element, we need to also have some agreements, some convention, and you need to keep it in mind. So the same scenario for tension and compression, we have the sign of positive and negative. All right? For shearing stress, previously I told you no sign, right? For shearing stress, always there is no sign. But we need to agree on something. So anytime we want to write down, instead of writing tau xy and then getting confused that if it is up or it is down, we just make an agreement. Shearing stress sign agreement. And this is our agreement. So we look at an element like this one, and we look at the vertical, basically, side. Stresses is something like that, or it might be something like that. All right? So it depends on the external loads and shearing stress. You're going to see soon the direction for the vertical plane again. It might be something like that. And always remember, if one side, the right side, is going up, the bottom side has to come down, right? Let me close my window because of background noise. All right, better. So, and the stress might be something like that. This is going to be our agreement. If we look at an element and these two stresses, we treat them more like a couple, and they try to rotate it counterclockwise, like this one, like a wheel, we try it, rotate it counterclockwise. We consider it positive. And if they try to rotate the element clockwise, we consider it negative. Right? This is, again, just an agreement between you and me. Later, when you saw something like that, you say the stress is positive. Something like the right side, you consider is negative. Okay? And always for an element, a 2D element, we have sigma x, sigma y, and tau xy. All right? Is it clear so far, guys? And if you're confused a little bit, wait a minute. Shortly, you're gonna see some example and you see where we are getting based on all this discussion. But if any part so far is unclear, please let me know. Because this portion of Mech 260, it's considered to be sort of difficult to teach, and I try to simplify it as much as possible. I wished somebody in the past taught me like this, because it took me a long time to figure out things on my own. If you read the textbook, you realize it hasn't been explained that simply. Or many teachers, they just say, well, we have an element, it's 3D, and these are the stresses, without explaining where they come from, right? And then nobody explain when we can consider an element 2D. But here you saw we have outer layer and we have a thin plate, all right? Let's solve examples together and see how we can basically deal with this stress element, okay? In this part of the module, our task is finding the stress element. And then the next part of this module will do different things with the element. But for now, the first and most important thing is to draw basically the stress element, all right? Let's do it. For a very, very simple case, we have a shaft and it is under compression. The question asks us to draw the stress element for this one. So first of all, we are in outer layer. If I'm in outer layer, good news, it's a 2D. So I draw my element. So this is gonna be, I just magnify it over here. This is my element, right? And then what do I have? Well, for this one, it seems this element is only under compression. So only I have sigma x, which is equal to P divided by A. All right, guys, that's all, nothing else. This is my stress. So sigma y is equal to 0, and there is no shear. Tau xy is equal to 0. This is all I need. And I know how to calculate sigma x, P over A. All right, that's the stress element, all we need to do for this one. Let's move on to another example. This is only this is under torsion. Okay, we want to draw the stress element for this one. Again, let me draw a bigger element here. This is the element. And for shearing stress, I've seen a student a little bit get confused. The way that you do it, look from one face, look at this T, and the one that I explained in previous lecture. Imagine lots of slices, lots of coins, which form this shaft, basically. Then they try to slide on top of each other. If you have lots of discs and you try to twist them, so the stress then on this side has to be like that. For shearing stress, think of it as more like a friction, right? So if you find the stress at one side, then the rest is just coming together. Because if the stress on one side of this element is going up like that, then absolutely this one has to come down to cancel it. Otherwise, things are not going to be balanced, right? If both of them are upward, then it means this element can move up, which is not possible physically. And if on this side, both sides, we have stresses, now these stresses try to rotate these things counterclockwise, but this thing is not possible, right? Things are not spinning inside this shaft. So it means I have to have stresses here and here. Try to rotate the element clockwise to cancel it. Therefore, this is my stress, tau, and this tau, we know how to calculate it. It's TR, or let's just write down TC divided by J. It's C is the radius here. Or TR, some textbook, they show it by R, some by C. So if you've seen variation somewhere, don't get confused. TRJ, all right? So this is the state stress for a 2D element outside a shaft. Question so far? Seems very simple, right? So let's spice things up a little bit. And now we have a scenario where we have a shaft under torsion and under tension. I let you guys to think about it and draw the stress element for me. While you're doing that, I'll try to draw things for you. So again, we are outside. We are okay with the 2D element. And now our job is to find out the stresses for these two elements. So step by step, we do it separately for each of them. We just solve two examples for each of these scenarios, but individually. Now we have combination of them, right? T is going to create a stress, which based on the direction that we can see, it's going to be like that. All right. And again, this direction is important to understand. Look at this T and imagine all of these as more disk, and this disk based on this direction for T is going up. So the stress on this side is up. If we find one, the rest is just coming together, all right? And stress here, P is create a normal stress, which is more like that, okay? So this is our stresses for this element. So this is tau, which simply can find out TR divided by J. And this is basically sigma, which is force divided by area, which is pi r squared. So in this example, sigma y is 0. We have only sigma x and tau xy. Very simple, right? Any questions so far? Are we good? If we are good, then let's make it even more complicated. Now we have, let's say what we have. You guys tell me. Emily, tell me, what do we have here?
We have torsional
Right.
at the ends. We also have an X and a Y component.
X and Y component, all right. And so between the four things that we learn, normal, stress, torsional, and bending. Do we have bending or no?
We might.
So it's a cantilever beam, right?
Yeah.
So thanks, Emily. So this 200-pound try to bend this shaft. So we have like an axial load, this 1,000-pound try to extend things. We have a torsion, that's obvious. And as Emily pointed out, we have a force in y direction. This force, 200-pound, it doesn't mean that it's going to create a sigma y. So that's different. We don't know, right? So we don't just say because we have a load in y direction, we're going to have a sigma y. You're going to see in a moment. But something that we for sure we know is this 200-pound try to bend these points like the whole shaft. But let's draw these stresses for this one and see how it looks like. All right, now let me open my window. It's getting hot now. I also turn on a fan, so if the background noise bothering you guys, please tell me. All right, so we want to draw the stresses for this element, all right? And we need to do it patiently so we don't get confused, right? We start with a simple one with this 1,000 pound. This 1,000 pound, it creates a stress, which is obvious. It is tension, and it is on this side of this element. All right, and we know how to calculate that one. That's easy. It's simply, let's call it sigma x is 1,000 divided by pi and the radius squared. All right, that's sigma x. We are good. What about this 5,000 pound? This 5,000 pound, it creates a torsional stress, which I can figure out one side, this one here. And if I know one side, the rest is coming together. I know one trick that always I check in the past when I was a student, always these arrows, they come together, the tip of the arrows or the tail of them, they are together, right? That's one way to check. And this one also, we can calculate it. That's easy. Tau xy, it is equal to Tc or Tr divided by J, which we have T, it is 5,000. R, the radius is ½ inch. And J, we just learned pi over 2 R4. Right? So that's about tau xy. What else we have? So let's deal with this 200 pound. This 200 pound try to bend these things, right? This 200 pound create a bending moment. Let me show it here. Bending, which this bending is equal to 200 multiplied by 8 inches, 1,600 pound inches. Do you agree, guys, that it tried to bend this shaft? This is something that you've seen before, right? This is something that you saw if you look from the side of this shaft, like the side view. So this side view, it's fixed to the ground, all right? And we have 200 pounds force here. All right, so if you have 200 pound force there, so you know that the reaction over here is going to be two reaction, AX, AY, and then it's going to be an M. All right, which this M is, I show it here, like the direction of bending, and this M is going to be, and this M in this blue in this diagram is the reaction. It's 200 multiplied by 8. So bending, we learned that creates bending stress, all right? So what is the bending stress? So this is the cross section. Let me draw the cross section here. Where is my cross section? Yeah, let's do it with this one. So this is the cross section. All right. So this cross section, and this is point A that we are discussing now. Here. Okay. So this cross section, where is my neutral axis? This is where it gets tricky. This is your neutral axis. Right? Neutral axis. My laptop's getting slow when it gets hot. So let's review it one more time. This is our cross section. This is point A, this point. All right. This 200 create a moment M, and we learned that when we have a moment, we have a stress, which is my divided by I. I is about the neutral axis, and neutral axis is about the centroid, point C at the center here. So now with this knowledge, what is sigma A? Sigma A is equal to, somebody can tell me? What is the Y? Do you remember, guys, what was the Y? Y was the distance between any point and neutral axis. What's the distance between point A and neutral axis? It is 0, right? So it means I don't have any bending stress at point A. And in fact, this is the element that we need to analyze. I let you guys to think about it for 10 seconds and see if it makes sense. So this is M. Let's now review it together. We have a tensional load. We have a bending load. This 200 cause bending at point A. And we have a torsion. For torsion, we know how the stress turn out, simple. This 1000 also is simple. But what about this 200? It's a vertical load. Do we have a sigma Y? So that's the question. We say, okay, this load 200 creates at point A a bending, but for bending we have this formula my divided by I. But this Y is 0. Y is the distance between any point that you want to find out the stress to neutral axis. That's why this is the state of stress for point A. So we call it state of stress for point A. All right? So now the question is getting a little bit tricky. It asks us, is this point the maximum stress? Or let me ask my question like this. If you build these things and you apply this load, at which point you think it's gonna start breaking or bending? It's gonna be, any guess? It's gonna be point A, the one mirror of it, or somewhere else?
Would it be the not the same spot, but that kind of circumference just closer to the top?
That's a very good point. So Tom is suggesting that if we apply this load, his guess is that this thing is going to break at this point, which I just showed it here, point A. Sorry, point B. Other people, do you agree? If this thing is going to break, it's going to be point A or point B?
B.
Yeah, Sajida? Sajida also confirmed it's going to be point B, which makes sense, right? Because look at the 2D view over here. This load, this bending load, try to bend it, and probably like the most critical point is going to be at the top over there, right? It's going to start breaking and tearing down from that point, not from like this point. This is point A. In fact, that's the safest point. Maybe not the safest, maybe the one below is the safest. So then let's quickly draw the, I need a couple of more minutes and then we're done. Let's draw the stress element for point B. I do it over the top here. So point B, let's do it quickly together. First of all, we are going to have that sigma x. Because there is no difference between point B and point A. All of them, they are under these 1000 load. All right, that's easy. So it's going to be 1000 divided by I. That's the same. Also, it's going to be the same shearing stress. There is no difference between point A and point B. So the same shearing stress, tau xy. All right. Now, here is important part, and an important part which I want you to pay attention. These 200 create a stress at point B, which is a bending stress. And this point B is here at the top, right here. This is point B. And what is the stress at point B? Sigma at point B is M radius, whatever it is, ½ inch divided by I. And it is positive, right? Remember, this is our y-axis. So it means I have another stress here, which is going to be positive, and that one is, I just write it down there, M divided by I, all right? And these two, they add together because we have one tension coming from there and another one from there. So therefore, it's equal to 1000 pi plus M, which we just found M, right? M is how much? 1600 divided by I, which we know how to calculate I. I for this guy is about neutral axis is pi over 4 radius power of 4. Right, guys? Do you agree on this one? This guy is positive because it's tension. And this one, we just found it positive. We just add them together. So as you can see, this element at B, the stresses, the shearing stresses is the same as A, but the axial stress on X is bigger. Now, I want you guys to go and think about it later for a stress element at point B. So point B, point C, which is like underneath here. This point C, try to draw the stress element for this point. Okay, which probably you can guess. Everything is the same as this point B at the top, except point C, like this point C, sigma C is M, and this Y is negative, right? Divided by I, okay? Yeah, try to draw it, knowing that the point C, this one is negative, it is under compression. Remember this, when you apply this load, you try to bend it. So point B is under tension, and opposite point, point C is under compression because of that load.